here at the Guinness factory in Dublin. Everybody thinks I'm here to shoot a funny remote segment, but actually, I'm just here for free Guinness. This was my idea. I don't care if we don't get 5 minutes of footage. I want free Guinness.
You may be interested to know that the inspiration for the t-test comes down to 3 simple words: brewing better beer. Back in the early 1900s, the Guinness Company would hire the best and brightest to help them brew better beer. And one of their stars was William Gossett, who developed the t-test as a way of checking the quality of their famous stout. But because of fear that competitors would steal their ideas, Guinness wasn't that thrilled about their scientists publishing their work, and had a rule that you could only publish if you, 1, didn't use your own name, 2, didn't mention Guinness, and 3, never talked about beer. So Gossett developed the t-test, and in 1908 published it under the pseudonym Student. Now, Gossett went on to be good friends with both Carl Pearson of the Pearson correlation coefficient and Ronald Fisher of the F-test, which is kind of interesting because Pearson and Fisher each had huge egos and really despised each other, but Gossett was friends with both, which is kind of cool. Now, what really kind of stinks is that because Gossett published under the pseudonym Student, it's technically the student's tea, not Gossett's tea. I suspect he downed more than a few pints of Guinness over that one. A one-sample t-test is very similar to a one-sample z-test, with a couple of key differences. If you're a little confused or haven't watched the one-sample z-test videos, it may be worth going back and watching them as well. For example, the purpose of a one-sample t-test is the same as a one-sample z-test. That is, to see if the population reflected in our sample has a mean that's different from some specified value. The population may be clear and easy to define, such as high school students in Wisconsin, or it might be something a little more theoretical, such as the population of people who might receive an intervention. Now, when you look at the assumptions for the one-sample t-test, they're almost the same as we saw for the one-sample z-test. First, the population needs to be normally distributed. Technically, like with the one-sample z-test, what I mean is that the population distribution for sample means is normally distributed. If I took an infinite number of samples and calculated a mean for each of those samples, would those means follow a normal distribution? Now, of course, the central limit theorem continues to apply here. If the sample size is larger than, say, 30, the answer is generally yes. The distribution of sample means will get closer and closer to normal regardless of the underlying raw distribution of the data. So with large samples, this assumption can often be a little relaxed. Now, if you're not sure about this, go back and watch the central limit theorem video again. Now, as we said before, it does make things easier if the underlying raw individual data follows the normal curve. In that case, you don't have to worry about what's large enough or how big of a problem is this. Think about it. If the scores for individual children follow the normal curve, then of course the sample averages based on any sample size will follow the normal curve. Even an average for a sample size of 1 will be normally distributed because individual scores are normally distributed. A second assumption is that the data reflect a random sample. Basically, everyone in the population needs to have the same chance of being in the sample, Otherwise, the sample can end up being biased in one way or another. Third, the data need to be on an interval or ratio scale, meaning that the units for whatever you're measuring are equally spaced. So far, everything is just like the one-sample z-test, but here's the difference. You use the one-sample t-test when you do not know the population variance. In this case, we have to estimate the population variance based on our sample, so we're using s squared for variance. Note that it's the lowercase s squared with n minus 1 in the denominator. Once you determine that a one-sample t-test is designed to answer your question, and you know that your data satisfies the assumptions needed to perform the test, you need to formulate your hypotheses. Now, just like many statistical tests, hypotheses in a one-sample t-test can be directional or one-tailed, or non-directional and two-tailed. First, consider a directional or one-tailed hypothesis. Directional hypotheses can go two directions. First, the alternative hypothesis can be that the mean for the population being sampled is greater than some score. Mathematically, this can be written as mu1 is greater than mu0. In that case, the null hypothesis is mu1 is less than or equal to mu0. Remember, mu0 is whatever value I think is the average for the population I'm studying if the null hypothesis is true. Alternatively, a one-tailed hypothesis in the opposite direction would be that the mean for the population being sampled is less than some score. Mathematically, this can be written as mu1 is less than mu0. In that case, the null hypothesis is mu1 is equal to or greater than mu0. Let's say that the average birth weight for all the babies born in the U.S. is 3,400 grams, but I don't know what the population standard deviation or variance are. And I want to test whether the average birth weight for babies born to mothers who don't have health insurance is less than 3,400 grams. In this case, my mu0 is 3,400 grams because if the null hypothesis is true, that's what I think the population average for babies whose mothers do not have health insurance will be. Mathematically, my alternative hypothesis is mu1 is less than mu0, and my null hypothesis is mu1 is equal to or greater than mu0. Plugging in values, you could also frame the alternative as mu1 is less than 3,400 grams, and the null hypothesis as mu1 is equal to or greater than 3,400 grams. Or in English, you can say that the alternative hypothesis is the mean when mothers have no insurance is less than 3,400 grams, while the null hypothesis is the mean when mothers have no insurance is equal to or greater than 3,400 grams. Now, instead of mu1 and mu0, you may see someone use mu and some other Greek letter, such as delta. And that's because you can compare the mean for the population being sampled, in this case, babies whose mothers don't have health insurance, with any value. It doesn't have to be the overall population mean. But the principle is still exactly the same. And of course, we can have a one-tailed hypothesis going in the other direction. In this case, where we think the mean for the population being sampled is greater than some value. But again, the principle is exactly the same. And finally, just like with one-sample z-tests, we can have two-tailed or a non-directional hypotheses where we're considering outcomes in either direction. Okay? So at this point, you've determined that a one-sample t-test is designed to answer your question, and you know that the data you have satisfies the assumptions that are needed to perform the test, and you now have your hypotheses. So how do you calculate your test statistic and determine the p-value? We'll cover that in our next video. Okay? Bye for now.